Hello everyone, welcome to Chapter 19, Planar Kinetics of a Rigid Body, Impulse and Momentum. In this module, we are going to discuss linear and angular momentum first. Basically, this is very similar to particles when we discuss this for rigid bodies. If you remember, the mass multiplied by the velocity represents the rigid body's linear momentum. The only difference now, instead of saying m times v, we're going to indicate v by vg, which is the velocity at the center of mass. And remember that this is a vector quantity, so you have to identify if this is done in which direction or on which axis. And if you remember, the angular momentum used to be h equals I g omega, and I is the mass moment of inertia, and omega is the angular velocity. And this is done at point G, for example, which is the center of mass. So nothing new with that regard. Now, let's use these two quantities into analyzing different kinds of motion. If I have translation only, that means the rigid body is moving in a line instead of rotating. Therefore, hg is cancelled. There is no angular momentum because there is no angular velocity, and I end up only with L equals mvg. So I only have linear momentum. If I have rotation about a fixed axis, and generally when we say rotation about fixed axis in the analysis, I'm considering the fixed axis to be a point other than the center of mass. So here I have point O, and here I have G. So these two are not the same. Therefore, the center of mass, when the object rotates, is going to have a velocity. Therefore, I have L equals mvg. And also because I have angular velocity, hg is going to equal to ig omega. So I'm going to have both. So either you use this one or that one. Another option is that instead of doing h at point G, you can do h, the angular momentum, at point O. In that case, you have to apply the parallel axis theorem, which says, I'm going to say Ig plus mr squared. And r is the distance between the center of mass and the point at which you are taking the momentum, which is point O. Therefore, r in this case is between O and G. And this gives me IO omega. General plane motion is the third case, and this happens when the center of rotation is not on the object itself. So the object is rotating around a point outside of its own body or outside of its own size. Therefore, it's the same thing. I'm going to have L equals mvg, and I'm also going to have hg equals ig omega. The only thing that you need to keep in mind that what is when you want to apply a parallel axis theorem, it does not apply here directly. So let's say the object is rotating around point A. Therefore, HA will equal to IG omega plus mvg times d. And I do not say, as in the previous case, I'm not saying IG plus mr square all times omega, because now the relation between V and omega is not with the same D. Therefore, it's Ig omega plus D multiplied by mvg, because Vg does not equal to, in this case, let me write it here, Vg does not equal to omega D. If Vg equals to omega D, then it will be Ig plus md square, which is the same as parallel axis theorem. Here you have to find where is the IC, which could be, for example, here. Maybe this is your IC, for example, and this will be a different distance than D. So you can call this one D, and you can call this one, let's say, L, for example. So it's not the same. Keep this in mind. Now, we want to apply these quantities that we have seen before into the principle of impulse and momentum. Basically, in case of particle motion, the principle of impulse and momentum for a rigid body is developed by combining the equations of motion. So it's the same as in the particle analysis. The resulting equations allow a direct solution to problems involving force, velocity, and time. So once you have these three components, you know that you are solving a problem with principle of impulse and momentum. And you're going to develop two sets of equations. One for linear impulse and momentum, and the other one for angular impulse and momentum. So it's the same equations. You have two linear impulse and momentum, exactly similar to particle analysis. The only difference is that the velocities are now at point G. Okay? And then you have the third equation, which is angular impulse and momentum around also either G, or you can do it around, let's say, point O, a different point. So here you have the option of doing it at two different points. Okay? So to solve the problem, the procedure is that first you have to establish the XYZ frame of reference or your coordinates. Draw the impulse momentum diagrams, which is similar to free body diagrams, showing the direction of all the forces acting on your object. Then you have to compute the mass moment of inertia as necessary. It could be IG, it could be IO, depending on what you need in that problem. And then you would apply the equations of impulse and momentum. Now, you might need to apply the linear as well as the angular equations, or you could apply only the angular or just the linear. It depends on the type of motion that you have. And keep in mind that these are three equations, so you can solve up to three unknowns. If it happens that you have a fourth unknown, more than three unknowns, then you have to rely on also kinematic equations to solve whatever unknown that you might have. So nothing new with the theory, just the way we apply it for rigid bodies. So let's start with the first example that we have. Gear A has a mass of 10 kilograms and a radius of gyration of 200 millimeters. And Gear B has a mass of 3 kilograms and a radius of gyration of 80 millimeters. The system is at rest when a couple moment m of magnitude 6 Newton meter is applied to Gear B. Neglecting friction, determine the time required for the angular velocity of Gear B to reach 62.8 radians per second. Secondly, find the tangential force which Gear B exerts on Gear A. That means the force that Gear B is forcing or applying on Gear A. So first of all, let's start with my coordinate system in this case. I could do something like this, saying that this is the positive x, or let me change it. I'm gonna use something more convenient for this problem. I'm gonna use these inclined. So let's do something like, I'm gonna do it inclined. So I'm gonna use, this is my x, this is my y, and this is my z. This is my rotation. Okay. So now let's look at the quantities that we may need. First of all, I have omega b. I need to find omega a. So it was given that omega b was given, so I need to find omega a. Now, at this point, so at this point, okay, the two gears should have the same velocity. So VA at that point should equal to VB. Okay, so I'm gonna utilize this. And again, this is my X, this is our Y, and this is our Z. So I'm gonna say VA should equal to VB, which gives me that omega A RA should equal to omega B RB. And this will give me that omega A should equal to RB, which is given in this problem as 100 millimeters. RA is 250. Okay, so 100, which is 0.1 over 0.25 times omega B, which is 62.8. This will give me that omega A should equal to 25.1 radians per second. So this is the first thing that I need from this problem. Second thing, let's compute IA and IB because I'm going to need them. Since I have the radius of gyration, it's going to be MA KA square. Mass is given for A as 10, radius of gyration is 200. So this equals to 10 multiplied by 0.2 square. And this gives me 0.4 kilogram meter square. Similarly, for IB, it's just the different values, but the procedure is exactly the same. So MB KB square equals to MB is given as 3 kilograms, radius of gyration is 80. So it's going to be 3 multiplied by 0.08 square. And this will give me IB as 0.0192 kilogram meter square. So now I have the values that I need in my problem. Next step, let's start with the impulse and momentum diagram. So I will start with A. Initially, I have gear A something like this, and there is only IA omega A, and it was omega A1 was 0, it was at rest. Okay, plus, so this is for the angular momentum. Plus, let's look at the forces acting. Gear B is pushing gear A. As you can see here, gear B will force a force like this on gear A. Therefore, I'm going to put this force acting downward in this case. So this is acting from B on A. And A has this effect on B. So I'm going to put this as a force multiplied. So this is force BA, from B acting on A. And I also have two reactions in here. Okay, you can have AX, AY. Okay, so these are the forces, and this should equal to the final angular momentum, which should be omega A2, something like this. Okay, so let's start now. I'm going to say I'm going to apply the angular impulse and momentum around point A. Okay, so around point A, I'm going to have H at A plus. So if you go back to the equations and you see what we have, I'm only going to apply this. And remember, I told you, instead of G, you can apply OA or whatever. We are using center of mass G directly. Okay, so A is my center of mass in this problem. So it's going to be HA plus integral of M dt, summation of M dt, whatever moments and forces I have, should equal to HA2. Now this will give me HA1 was 0. Now let's look around point A. The two reactions do not give me any moments, only the force FAB, and it should be multiplied by the radius R, RA. So it is giving me, if you look at the sign convention here, it's giving me a negative moment. So it's going to be minus FBA times RA. And remember, this is the moment. You have to multiply by the time to make it momentum. To make it angular impulse. So it's FR times T. Okay. This should equal to, again, my convention here is clockwise and positive is counterclockwise. So it's going to be minus IA omega A 2. Okay. So if I apply this, the minus will cancel from both sides. And I will have RA, which is 0.25 FBA times the time T should equal to 0.4 multiplied by 25.1. And this will give me that FBA times T together, this multiplication will give me 40.2 Newton second. So this is the first thing that I get out of this equation. Now I'm going to do the same thing for B. So in this case, I have B, originally at rest, so it was 0, no rotation, plus, let's look at the forces acting on it now. So this force is opposite, okay? So it is F B. This is opposite to the force B acting on A. That's why I'm using BA. If you write it AB, there is no mistake in there. And we also have the applied moment, and we also have two reactions, Bx and By. And this should equal to the final motion of the object, so it's going to be omega B2. And I'm going to write the same thing. I'm going to take this is positive again around point B. So I'm going to say H B1 plus summation integral of M dt should equal to H B2. So what do I have? I have 0. And then let's look at the moment. It's counterclockwise, so it's positive. And the moment was given as 40.2, so it's plus. Sorry, the moment was not 40.2. The moment was equal to 6 Newton meter. Okay. So I'm going to say plus 6 Newton meter times the time t, which is unknown. And then I have the force FAB is giving me counterclockwise moment. So it's going to be minus F times t. I don't know the value of F, but I know that F times t equals to 40.2. So I'm going to say minus 40.2 multiplied by RB. Don't forget, which is 0.1. This should equal to IB, which is 0.0192 multiplied by omega B2, which we know it as 62.8. Okay. Now, as you can see here, that the only thing unknown is the time, and I can solve the time, and I will get the time to be equal to 0.871 seconds. Now, going back to find the force that is applied, remember we know that F times T should equal to 40.2. Therefore, substitute the time in there, and you will get F BA or AB, depending how you want to write it, will equal to 46.2 Newton. Okay, and that's the two requirements of the problem. Now let's look at the second example. If the cord is subjected to a horizontal force of 150 Newton as shown, and the gear is supported by fixed pin at O, meaning that the gear does not move in a general plane motion, it is rotating around O. Determine the angular velocity of the gear and the velocity of the 20 kilogram gear rack that is in the bottom in 4 seconds, starting from rest. The mass of the gear is 50 kilograms and it has a radius of gyration of 125 millimeters. Assume that the contact surface between the gear rack and the horizontal plane is smooth. Okay? So, the first step now is to establish your diagram, establish your coordinates and draw your diagram. So, I'm going to say my coordinates, I'll use this as X, I'll use this as my Y. And my rotation I'm gonna use, it's up to you, I'm gonna use this as my Z. You can choose what is convenient, because I know from the applied force it's gonna rotate clockwise, so I'm gonna use that as my positive. Now next thing is to look into the diagram, free body diagram or impulse diagram. So let's say this is my gear, okay, and this is the inner part. So I have force P here, okay. I also have the weight acting downward, okay, which is the mass times gravity. Then it is 50 multiplied by 9.81. I also have, if you look at this problem, the gear is going to rotate something like this. So the gear is going to push this rack in this direction, and the rack is going to give an opposite force in that direction. So I'm going to put the force to the right. Okay, so this is force F, which I don't know the value of that one. And we also have two reactions at the pin. So the pin was called point O, so I'm going to have OY and OX. Okay. So these are the forces acting on my object. Now, let's calculate IO since I'm going to use it. I at O will equal to M K around O square. So this will equal to 50 multiplied by 0.125 square. Let me check the value was given. So KO was 125 millimeters, so we write it as 0.125 meters squared, and this will give me a value equal to 0.78125 kilogram meter square. Now, let me write the angular impulse and momentum equation. I'm going to use this is as positive, okay, or I can use the other as positive. Sorry, if we are doing this, then let me change it. Doesn't matter. You can choose whatever that you feel comfortable with. Just forgot that I chose that one. So let's do it this way. Okay. So if this is positive, I'm gonna write I O omega 1 I omega plus summation of M dt should equal to I O omega 2. Okay. Now it was originally at rest, so this is 0. Now let's look at the forces and moments acting on this. Force F is going to give me a positive impulse because it's going to give me counterclockwise. So it's going to be plus the force F multiplied by the radius to make it a moment. And the radius in this case will be from here to here, which equals to 150. Okay. So F times 0.15 times the time, which was given as 4 seconds. And then I have force P is giving me clockwise, which is negative. So it's going to be minus 150. Then the radius to make it a moment, which is 75. So it's going to be 0.075. And then also don't forget to multiply by the time to make it an impulse. The weight and the two reactions, they pass through point O, and therefore they do not give me any angular impulse. So this should equal to 0.78125 omega 2, which is unknown. Okay, so this gives me an equation that has two unknowns. F will equal to 75 minus 1.302 omega 2. So this is one equation that has two unknowns. Now I can go to another equation now, and I'm going to do linear impulse and momentum for the rack at the bottom. So if you remember, we said that this is X, this is Y, and this is Z. Now the rack at the bottom, remember the force was acting to the right, therefore here it's going to act to the left. So this is my force F. I have the weight, which is 20 times 9.81, and I also have a normal force acting in here. So if I choose, let's say, right is positive, and I'm gonna say m v1 plus summation of f dt. I'm just writing the principle of linear impulse and momentum should equal to mv2. Now, it was originally at rest, so this is 0. F is acting opposite to the left, so it's going to be minus force F, which is unknown, multiplied by the time, which is 4. Now, the weight and the normal force, they are acting vertical, so they do not give me any impulses on the horizontal direction. And this should equal to, I know the object is going to move to the left, so it's going to be negative, so it's going to be minus 20 V2. Now, let's look at this problem. So this is the gear, okay, and it has this point, okay, which is acting on this rack. So these 2 points, okay, should have the same velocity, right? So these 2 points should have the same velocity because they are the same point. Therefore, if I can relate this velocity, okay, to omega of that object, then I can have the 2 as one unknown. So I can write it now as, let's call this point A. So I'm going to call this point as point A, just for the sake of, discussion. So I'm going to write VA from here. Okay, VA should equal to omega of the gear times R, which equals to, this case, 0.15 times omega. So I'm going to use this as my V2 in this case, because the point is shared. So back to that point, I'm going to say 4F, just take the minus out, it's going to be equal to 20 times 0.15 times omega 2. Okay. In this case, I will have F should equal to 0.75 omega 2, and this is my second equation with the 2 unknowns. So this was equation 1, and this is equation 2, 2 equations with 2 unknowns, and I can solve the output. Okay, in this case, solving the 2 equations will give me that omega 2 should equal to 36.5 radians per second. Okay, now keep in mind that the problem asked you to find the velocity. So determine the angular velocity of the gear, which we did, and the velocity of the 20 kilogram gear rack. Remember that we said V equals 0.15 omega, so I'm going to calculate this, the velocity of the rack, which is point A, should equal to 0.15 times 36.5, and this will equal to approximately 5.48 meters per second to the left. Okay, and this concludes this module. I hope that it was useful to you and that you enjoyed it, and I wish you the best of luck with your studies. Thank you.